Why do 60% of high-performance plastics fail under extreme conditions? Today we're solving the mystery. Plastics are everywhere. From the packaging that keeps our food fresh to the high-performance gears in industrial machines, polymers are essential to our lives. But here's the kicker. Some plastics, like polypropylene, degrade when exposed to ionizing radiation. A real bummer for durability, right? Well, hold on to your lab coats. Researchers have found a game-changing solution. By integrating polyethylene terephthalate nanoparticles into polypropylene, they've significantly boosted its resistance to thermal aging and mechanical breakdown. Imagine this. Blending just 10% of these nanoparticles can make polypropylene withstand extreme conditions, extending its lifespan. Think aerospace, medical, and beyond. This could revolutionize how we use plastics in high-stakes environments. Pretty neat, huh? Thanks for tuning in to Science Salah Lotfy channel. Don't forget to like and subscribe for more cutting-edge science. Hey there, science enthusiasts. Welcome to For Science Salah Lotfy channel. Today, I'm diving into an innovative study from the journal Polymer Degradation and Stability. It's all about how PET nanoparticles can transform the durability of polypropylene when exposed to electron beam irradiation. Intrigued? Let's get into it. This groundbreaking research was conducted by some brilliant minds, Associate Professor Mohamed Elhady and Professors Ahmed Elbarbary, Yasser Gad, and Fathy. They're from the Radiation Research of Polymer Chemistry Department at the National Center for Radiation Research and Technology in Cairo, Egypt. Their study focuses on enhancing the durability of polypropylene under ionizing radiation. Now, why is this important? Polypropylene is super popular in industries because it's lightweight, moisture-resistant, and cost-effective. But it really struggles when exposed to ionizing radiation, which weakens its structure over time. The researchers found a way to tackle this by integrating polyethylene terephthalate, or PT nanoparticles, into polypropylene composites. They examined the effects of electron beam irradiation at doses from 25 to 100 kg. They looked at key mechanical properties like tensile strength, elastic modulus, elongation at break, and hardness. Plus, they conducted thermal aging tests at high temperatures of 75 and 100 degrees Celsius to check the longevity of the modified polymer. So what did they find? Adding 10% PET nanoparticles to polypropylene showed the best results. It significantly improved thermal and mechanical stability, extending the material's lifespan under extreme conditions. This has big implications for industries that need high-performance thermoplastics like aerospace, automotive, and medical fields. This pioneering research opens new doors for developing radiation-resistant materials, boosting sustainability and improving material efficiency across many sectors. If you found this as fascinating as I did, don't forget to like, share, and subscribe to For Science Salah Lotfy channel for more groundbreaking scientific discussions. Hey there, science fans! Today we're talking about a fantastic material called polypropylene, or PP for short. It's everywhere. Your lunchbox? Probably made of PP. That cool car part? PP again? From toys to medical devices, PP is a superstar. Why? Because it's strong, lightweight, and doesn't cost a lot to make. But even superheroes have weaknesses. PP's biggest problem? It doesn't like radiation. You know, those invisible rays that can be harmful? Exposure to radiation can make PP weak and brittle. That's a bummer, especially for things like medical equipment that need to be super strong and safe. So, how can we protect our plastic pal PP from those pesky rays? That's where some clever scientists stepped in with a brilliant idea. Imagine this, you have a fantastic spaceship made of PP ready to explore the galaxy. But wait, space is full of radiation. Over time, those rays would weaken your spaceship, putting your mission in jeopardy. That's the challenge scientists wanted to solve. They knew PP was great, but its weakness to radiation held it back from being even more awesome, especially for things like space travel, medical equipment, and nuclear power plants. These brave scientists had a plan. They wanted to find a way to make PP stronger and more resistant to radiation damage. They turned to a surprising source, tiny particles called nanoparticles. Have you ever heard of PET? No, not the furry kind. We're talking about polyethylene terephthalate, the plastic used to make soda bottles. It turns out that PET can be transformed into incredibly small particles called nanoparticles. Think of them as microscopic superheroes. These PET nanoparticles are so small that you need a super powerful microscope to even see them. But don't let their size fool you. They are incredibly strong and can make other materials much tougher too. Scientists had a hunch. What if they could mix these tiny PET superheroes with PP? Could they create a super strong plastic that could withstand even the harshest radiation? it was time to put their hypothesis to the test. Section 4. Mixing it up. Creating super strong plastic. Picture a scientist in a lab coat, carefully measuring out ingredients. Instead of flour and sugar, they are using PP and PET nanoparticles. Their mission to combine them in just the right way to create a super material. Using special techniques, the scientists blended the PET nanoparticles with the PP. Imagine mixing sprinkles into your cake batter. The nanoparticles spread evenly throughout the PP like tiny reinforcing agents. It was like giving the PP an invisible shield of armor. Now came the moment of truth testing time. The scientists created samples of their new PP PET nanocomposite material and prepared to face them with the ultimate challenge: radiation. Section 5. Facing the radiation, the ultimate test. To simulate the harsh environment of space or a nuclear reactor, the scientists used a powerful tool called an electron beam. This beam shoots out invisible rays, similar to the radiation found in those extreme places. The scientists carefully aimed the electron beam at their PP PET nanocomposite samples. They wanted to see how well the material could withstand the radiation. Would it crack under pressure? Would it become weak and brittle? Or would it emerge stronger than ever? After the radiation treatment, the scientists eagerly analyzed the samples. They used sophisticated instruments to study the material's structure and properties. The results were about to be revealed. Section 6. Surprising results, stronger than ever. The scientists were amazed by what they discovered. The PP PET nanocomposite had passed the radiation test with flying colors. The PET nanoparticles had worked their magic, making the PP incredibly strong and resilient. Even after being bombarded with radiation, the nanocomposite material remained tough and flexible. It didn't become brittle or break down like regular PP. It was like the PET nanoparticles had formed a protective barrier, shielding the PP from the damaging effects of the radiation. The scientists celebrated their groundbreaking discovery. They had successfully created a super strong, radiation-resistant plastic with incredible potential. Section 7. The future is here. Endless possibilities. The implications of this research are enormous. Imagine lighter and safer medical equipment that can withstand sterilization by radiation. Picture spacecraft and satellites that can endure the harsh conditions of space for longer missions. Think about more durable and reliable components for nuclear power plants. The possibilities are endless. This incredible PP PET nanocomposite has the potential to revolutionize industries from healthcare to aerospace and beyond. Thanks to the power of nanotechnology, we are entering a new era of stronger, more resilient materials that can help us explore new frontiers and create a brighter future. Stay curious, science fans. Space is vast, it's full of wonders, but some of the most exciting discoveries aren't light years away. They're happening right here on Earth in the world of materials science. For centuries, we've built with what nature provides: wood, stone, metal. These materials shaped our past. But to reach for the stars, we need something more. We need materials that are stronger, lighter, and more durable. This is where the nano world comes in. By manipulating materials at the atomic level, we can unlock incredible properties. We can create nanocomposites that outperform anything found in nature. One exciting area of research is PP/PT nanocomposites. These materials hold the potential to revolutionize industries from packaging to aerospace. Let's explore how these tiny wonders are made and why they are so promising. PP PET nanocomposites start with two common plastics, polypropylene PP and polyethylene terephthalate PET. You know them. They're in countless everyday products. PP is known for its flexibility. It's often used in food containers and packaging. PET, on the other hand, is strong and transparent. Think water bottles and clothing fibers. But what happens when we combine them at the nanoscale? We create a material that's greater than the sum of its parts. To do this, we first need to modify the PET. We break it down into nanoparticles, tiny particles with remarkable properties. We use a special ingredient called maleic anhydride. This helps the PET nanoparticles bond tightly with the PP. The result is a nanocomposite with enhanced strength, flexibility, and heat resistance. Now imagine a beam of electrons, invisible but incredibly powerful. This is the key to further enhancing our nanocomposite. Electron beam irradiation is like giving our material a boost of energy. It causes changes at the molecular level, creating even stronger bonds between the PP and PET nanoparticles. Think of it like baking a cake. The heat of the oven transforms the batter into a delicious treat. Similarly, the electron beam transforms our nanocomposite, improving its properties. This process increases the material's tensile strength. This means it can withstand greater force before breaking. It also improves its thermal stability, making it suitable for use in high-temperature applications. Section 4. Testing the limits. Creating a new material is just the first step. We need to put it through rigorous testing to understand its true potential. Tensile strength testing is like a tug-of-war for materials. We pull on the nanocomposite from both ends to see how much force it can withstand before breaking. Thermal stability tests are like a high-stakes sauna. We expose the material to extreme temperatures to see how it holds up. These tests tell us how the nanocomposite will perform in real-world applications. The results are impressive. PP-PET nanocomposites exhibit superior strength, flexibility, and heat resistance compared to conventional plastics. Section 5. A future built on nanocomposites. The future of material science is happening now. PP-PET nanocomposites are just one example of the incredible advances being made. These materials offer numerous benefits. They are lightweight yet strong, making them ideal for use in automobiles and aircraft. Their enhanced thermal stability makes them suitable for electronics and packaging. Imagine a world with lighter cars that use less fuel. Picture food packaging that keeps products fresher for longer. These are just a few of the possibilities that PP-PET nanocomposites offer. As we continue to explore the nano world, we can unlock even more incredible materials. The future is bright, and it's being built with nanocomposites, one tiny particle at a time. Our universe is filled with wonders, from the vast expanse of space to the intricate workings of the atom. In the realm of materials science, a new star is emerging, the PET nanoparticle. These tiny particles, measured in billionths of a meter, hold immense potential to revolutionize the world around us. PET, short for polyethylene terephthalate, is a familiar material found in everyday objects like plastic bottles and clothing fibers. But when manipulated at the nanoscale, PET transforms into a powerful ingredient for enhancing the properties of other materials, particularly polymers. Imagine a world where plastics are stronger, lighter, and more resistant to damage. This is the promise of PET nanoparticles. By incorporating these tiny particles into polymer composites, scientists are unlocking a new era of material performance. From improving the strength and durability of everyday plastics to creating advanced materials for aerospace and biomedical applications, PET nanoparticles are poised to leave their mark on the world. Join us as we delve into the fascinating world of these tiny particles and explore their vast potential. To understand the power of PET nanoparticles, we must first journey into the microscopic world where they reside. Here, powerful tools like transmission electron microscopy, TEM, and dynamic light scattering, DLS, act as our telescopes, revealing the size and shape of these minuscule particles. TEM allows us to see individual PET nanoparticles appearing as tiny spheres on the screen. These spheres, typically ranging from 20 to 100 nanometers in diameter, are like the building blocks of a larger structure. Imagine a single grain of sand, now shrink it down thousands of times, and you'll have an idea of the size of a PET nanoparticle. DLS, on the other hand, measures the movement of nanoparticles in a solution. By analyzing how light scatters off these particles, DLS provides insights into their size distribution. This technique reveals whether the nanoparticles are uniform in size or if there's a range of sizes present. Both TEM and DLS are crucial for characterizing PET nanoparticles, providing complementary pieces of the puzzle. By combining the information from these techniques, scientists gain a comprehensive understanding of the size and structure of these tiny particles, paving the way for tailoring their properties for specific applications. Venturing deeper into the nano realm, we employ X-ray diffraction, XRD, and Fourier transform infrared spectroscopy, FTIR, tools that allow us to decipher the inner architecture of PET nanoparticles. Think of XRD as shining a powerful flashlight through a crystal, revealing the arrangement of atoms within. XRD patterns reveal the crystalline structure of PET nanoparticles. Just like stars clustered in constellations, the atoms within these particles arrange themselves in ordered patterns. These patterns dictate the nanoparticle's mechanical strength, thermal stability, and even its interaction with other materials. FTIR, on the other hand, identifies the chemical bonds present within the PET nanoparticle. Like fingerprints, each type of bond absorbs infrared light at specific frequencies. By analyzing the absorption patterns, scientists can determine the types and arrangements of chemical bonds, providing further insights into the nanoparticle's properties and behavior. Together, XRD and FTIR act as powerful decoding devices, revealing the intricate structural makeup of PET nanoparticles. This knowledge is crucial for understanding how these particles interact with their surroundings and how their properties can be fine-tuned for specific applications. Imagine a world where plastics can withstand the harsh effects of radiation, remaining strong and reliable even in extreme environments. This is the promise of PET nanoparticles, acting as tiny shields within polymer composites. Polypropylene, a widely used plastic, is susceptible to degradation when exposed to radiation. This degradation can lead to a loss of strength, flexibility, and overall performance. But when PT nanoparticles are introduced, they act like miniature guardians, absorbing and dispersing radiation energy. This protective effect is evident in the gel content of polypropylene. Gel content is a measure of cross-linking between polymer chains. Higher gel content indicates a more robust and stable material. Studies have shown that incorporating PET nanoparticles into polypropylene increases its gel content after exposure to radiation. This enhanced stability arises from the unique ability of PET nanoparticles to absorb and dissipate radiation energy. They act like tiny sponges, soaking up harmful radiation before it can damage the surrounding polypropylene matrix. This radiation shielding ability of PET nanoparticles opens up new possibilities for using polypropylene and other polymers in applications where radiation resistance is critical, such as in medical devices, nuclear power plants, and even spacecraft. Section 5. Stronger Together. Boosting mechanical properties with PET nanoparticles. In the world of materials science, strength and flexibility are highly sought-after qualities. PET nanoparticles, when added to polymers like polypropylene, act like microscopic reinforcing agents, enhancing both these properties. Tensile strength, a measure of a material's resistance to breaking under tension, is significantly improved with the addition of PET nanoparticles. Imagine pulling on opposite ends of a rubber band. The harder you pull before it breaks, the higher its tensile strength. PET nanoparticles act like tiny anchors within the polymer matrix, distributing stress and preventing premature failure. Similarly, the elastic modulus, a measure of a material's stiffness, also sees a boost with PET nanoparticles. This means the composite material becomes more resistant to deformation under stress. Think of pressing on a spring. The stiffer the spring, the higher its elastic modulus. PET nanoparticles with their strong intermolecular forces contribute to this enhanced stiffness. These improvements in tensile strength and elastic modulus are attributed to the strong interfacial adhesion between PET nanoparticles and the polypropylene matrix. This strong bonding creates a more unified and robust material capable of withstanding higher stresses and strains. The result is a new generation of polymer composites that are stronger, more durable, and capable of withstanding demanding applications. Section 6. The future is nano-potential applications of PET nanoparticles. As we continue our exploration of PET nanoparticles, we find ourselves standing on the threshold of a new era in materials science. The unique properties of these tiny particles, from their radiation shielding capabilities to their ability to enhance mechanical strength, open up a universe of potential applications. Imagine lightweight but incredibly strong plastics used in aircraft and automobiles, reducing weight and improving fuel efficiency. Envision medical implants that are not only biocompatible, but also resistant to degradation from sterilization techniques, leading to longer-lasting and more reliable medical devices. The possibilities extend beyond Earth. Radiation-resistant polymers reinforced with PET nanoparticles could be instrumental in constructing spacecraft and habitats for future space exploration missions, protecting astronauts and equipment from harmful cosmic radiation. In the realm of electronics, PET nanoparticles show promise in enhancing the performance of flexible displays and lightweight energy storage devices. Their ability to improve the mechanical and thermal properties of polymers makes them ideal candidates for these demanding applications. The journey of PET nanoparticles has just begun. As researchers delve deeper into understanding and tailoring their properties, we can expect to see even more innovative applications emerge, shaping the future of materials science and impacting numerous industries. Section 7. Challenges and Opportunities. Exploring the unknowns of PET nanoparticles. While the potential of PET nanoparticles is vast, our journey into the nano realm is not without its challenges. Like explorers charting unknown territories, scientists are constantly pushing the boundaries of knowledge, uncovering both new opportunities and areas that require further investigation. One challenge lies in controlling the size and distribution of PET nanoparticles during synthesis. Achieving uniformity in size and dispersion within the polymer matrix is crucial for optimizing their performance. Imagine baking a cake where the flour is not evenly distributed. The result would be less than ideal. Similarly, the effectiveness of PET nanoparticles relies on their uniform incorporation within the host material. Another area of exploration is the long-term behavior of PET nanoparticles within polymer composites. Understanding their stability over time, particularly under various environmental conditions, is essential for ensuring the longevity and reliability of these materials. Despite these challenges, the opportunities presented by PT nanoparticles far outweigh the obstacles. Researchers are constantly developing new techniques for synthesizing and functionalizing these particles, tailoring their properties for specific applications. The exploration of PET nanoparticles is a testament to the inquisitive nature of science. As we delve deeper into the nano realm, we unlock new possibilities and pave the way for technological advancements that can benefit humanity and shape the world around us. Section 8. From Lab to Life. The journey of PET nanoparticles into real-world applications. The journey of a scientific discovery from the laboratory to our everyday lives is an exciting one, filled with innovation and collaboration. For PET nanoparticles, this journey is well underway, with promising advancements bridging the gap between research and real-world applications. One example is the development of radiation-resistant plastics for medical devices. By incorporating PET nanoparticles, scientists have created materials that can withstand the rigors of sterilization processes without compromising their mechanical properties. This breakthrough has led to the development of longer-lasting and more reliable medical implants, improving patient outcomes. In the automotive industry, the use of lightweight and high-strength polymer composites reinforced with PET nanoparticles is gaining traction. These materials offer the potential to reduce vehicle weight, leading to improved fuel efficiency and reduced carbon emissions. Imagine a future where cars are not only more environmentally friendly, but also safer due to the enhanced crashworthiness of these advanced materials. The journey of PET nanoparticles from the lab to real-world applications is a testament to the collaborative spirit of science and engineering. As researchers continue to unlock the full potential of these tiny particles, we can expect to see their impact grow across various industries, shaping the world around us in remarkable ways. Section 9. Conclusion. The expanding universe of PET nanoparticles. As we conclude our journey through the fascinating world of PET nanoparticles, it's clear that we've only just begun to explore their vast potential. Polypropylene is a fantastic material. It's everywhere. From food containers to car parts, its versatility is remarkable. But polypropylene has a weakness. It breaks down easily with heat. Scientists are always looking for ways to make it stronger and last longer. One promising approach is mixing polypropylene with something even stronger. Polyethylene terephthalate, PET, nanoparticles. Imagine these nanoparticles as tiny, powerful shields protecting the polypropylene. To understand how well this protection works, scientists use a clever technique called thermal gravimetric analysis, or TGA. Imagine a tiny scale that heats up a material and measures how much weight it loses over time. This weight loss tells us how quickly the material breaks down. By comparing the TGA results of pure polypropylene with the polypropylene PET nanocomposite, we can see the remarkable impact of those tiny PET shields. The nanocomposite shows significantly less weight loss, meaning it's much more resistant to heat degradation. But the story doesn't end there. Scientists also use electron beam irradiation to modify materials. Imagine firing tiny energy beams at the polypropylene like microscopic darts. This can improve its properties, but it can also make it more susceptible to heat. The good news is that even with electron beam irradiation, the PET nanoparticles continue to protect the polypropylene. The TGA results show a remarkable difference in degradation rates, proving the effectiveness of this nanocomposite. Section 4, PET nanoparticles, tiny reinforcements with a big impact. So, how do these PET nanoparticles work their magic? Think of it like this. Polypropylene molecules are like long chains and heat can break them apart. But when we add PET nanoparticles, they act like tiny anchors, holding those chains together and making them much harder to break. This interaction between polypropylene and PET nanoparticles is the key to the nanocomposite's impressive thermal stability. Even at high temperatures, the material maintains its integrity and resists degradation, opening up a world of possibilities for its use. Section 5. A synergy of strength molecular interactions and enhanced thermal resistance. The secret lies in the molecular interactions between polypropylene and PET. These interactions create a strong bond like a microscopic handshake that prevents the polypropylene chains from moving freely and breaking apart under heat. This enhanced stability is evident in the TGA results, showing a significant delay in the onset of degradation for the nanocomposite compared to pure polypropylene. This breakthrough has exciting implications for various industries. Imagine lighter and more durable car parts, medical devices that can withstand sterilization procedures, and food packaging that keeps products fresher for longer, all thanks to the enhanced thermal stability of PP PET nanocomposites. The future of materials science is looking stronger and more resilient than ever before. Hey there, science enthusiasts! Welcome back to the For Science Salah Lotfy channel. Today I've got some fascinating research to share with you on how polyethylene terephthalate, or PT nanoparticles, are enhancing the stability of polypropylene. It's a mouthful, but don't worry, I'll break it down for you. So this research paper, titled Synthesis and Impact of Polyethylene Terephthalate Nanoparticles on the Stability of Polypropylene Exposed to Electron Beam Irradiation, was published in Polymer Degradation and Stability. It's quite a title, right? This study comes from the brilliant minds at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority in Cairo, Egypt. The team includes Associate Professor Mohamed Elhady, Professor Ahmed Elbarbary, Professor Yasser Gad, and Professor Fathy. Special shout out to Professor Ahmed Elbarbary, the corresponding author. Now let's get to the juicy details. The research dives into how electron beam irradiation and PET nanoparticles can significantly improve the thermal and mechanical stability of polypropylene, or PP for short. Think about it. Stronger, more durable plastics. This could revolutionize industries that rely heavily on polypropylene. Key terms you need to know from this study include electron beam irradiation, mechanical properties, thermal analysis, and thermal aging. It might sound technical, but the bottom line is that these enhancements could lead to advanced applications and more robust materials in various fields. A massive thanks to the researchers for their groundbreaking work. Their dedication to pushing the boundaries of material science is truly inspiring. And of course, thank you for tuning in. If you found this as intriguing as I did, drop your thoughts in the comments below. Let's chat about the potential impacts of this research. Don't forget to like, share, and subscribe for more scientific insights. See you in the next episode on For Science Salah Lotfy channel. Thanks for watching.